Yeah, I noted in the program that it was noted just as early every day at 9 a.m., right? So yes, I think I have the task 4 days this week to wake you up in the morning. No, I don't think it is. But what I say now doesn't need to be recorded, so it's okay. But this is on. This is on. Okay, anyway, while we're waiting, so a significant fraction of this lecture is going to be on the blackboard. So if you can't see well from the back, now is your chance to come a bit up front. And I also encourage you to take notes, right? So if you have pen and paper, that will be helpful. Should we just start? Yeah. I'll just take this off and then we... What, do you want me to keep it on in case it starts work? Should I keep it on in case it starts working?
Let's yeah, take it off.
Take it off, okay.
Come back to life.
Yeah,
Well, then, yes. Then we'll stop in the middle. Okay, good.
Okay, so with that, let's get started. So the topic of these lectures are going to be early universe, which is a topic. So what I decided to talk about is I want to go backwards. So I want to start with this lecture today with CFD decoupling and VBM. And that's basically going to be the only lecture where I tell you about stuff that we actually know. And after that, it starts to get hypothetical, right? So then we go earlier in time, we talk about baryogenesis tomorrow. And then the last two lectures will be dedicated to inflation. And this is basically how we will do it, because I wanted to give a blackboard lecture, but due to limitations of the blackboard, right, I'm going to be largely writing on the blackboard for all the things that I want to write equations, I want to go a bit slow. Give you enough chance to ask questions, feel free to ask questions during the lecture. And then when there's stuff which have a bit more text, we'll do it with the slides, but it will all be at a pace that you can actually take notes if you want to take notes. And you can kind of see on the slide, you can see what the structure of the lecture would be on the blackboard if I had a blackboard. So you can make it nice in your notes. Okay. Okay, so starting point for basically everything in the early universe is Einstein's equations. And Einstein's equations, let me just write them here again. So we have on the left-hand side R mu nu, the Ricci tensor, G mu nu is the metric, R is the Ricci scalar, and then on the right-hand side, G is Newton's constant, and we have the energy density. And what Einstein's equations do is they relate everything depending on the metric on the left-hand side, with everything depending on the content of the universe, the matter, on the right-hand side. So this Ricci tensor and the Ricci scalar are functions of the metric. You can compute them using the Christoffel symbols, but everything that goes onto the left-hand side is metric. And here we put the energy density of the universe. So what this equation tells us is how the energy density of the universe impacts the metric, and also then how the metric impacts how the matter behaves. Now, this is a complicated equation. When we do cosmology, we simplify things a lot. So what we do is on the left-hand side, on the metric side, we're going to make the ansatz of homogeneity and anisotropy, right? So on the left-hand side, which is the metric, we're only going to consider, at least for the first 3 lectures, an FRW metric, right? So a Friedman, Robertson, and Walker metric, which means that ds squared, so the proper distance, is given by dt. And then here we have the scale factor as a function of time. This tells us the expansion of any box in the universe. And then here we have the volume, where so the omega is just the usual angular part. So this would just normally be d3r, apart from this k here. This k is the curvature. It can take values 0, -1, +1. In our current universe, it's 0. And for basically most of these lectures, we will be ignoring it. And when we come to inflation, I will be explaining to you why we're ignoring it, so why we're setting it to 0 in the late universe. So that's what we do on the left-hand side. And then on the right-hand side, this is not writing very well. Let's try another one. On the right-hand side, the assumption that we're going to do is we're going to assume a perfect fluid. Which means we're going to write the energy momentum tensor as a diagonal, with the first component being the energy density, and the last 3 is the pressure. So I should maybe say that my metric convention is going to be plus, minus, 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 which is why we have the minus signs here. And okay, the universe obviously today is not a perfect fluid, right? You look out in the universe, it's clearly not a fluid. But at early times, it actually is to good approximation. And we can consider different types of fluids, depending on what is the matter content of the universe at any given time. But for example, if we take a gas of relativistic particles, which is the case in the very early universe, so if we have relativistic particles, then, for example, you have a Fermi-Dirac or Bose-Einstein distribution, and you can directly compute the energy density and the pressure. So I'll give you the expressions because we'll need them later on during these lectures. So for example, if we compute the energy density using Bose-Einstein distribution, right, for every boson, and using Fermi-Dirac for every fermion, so NB counts a number of bosonic degrees of freedom, and F counts numbers of fermionic degrees of freedom. And then here we get pi squared t to the 4 divided by 30. So you can get this directly by just performing the integration over the distributions, or you can go back to the partition function and do proper thermodynamics, and you will get the same response, of course. The same way you can get the pressure, the prefactor is always the same. And now there will be an extra factor 1/3 for a relativistic gas. And then also we will need the entropy, which again has the same prefactor. And here now that has the scale as t to the 3 with some different order 1 coefficients. Okay, and so now we have simplified the right-hand side, simplified the left-hand side, and only with those assumptions we get now to the famous Friedman equations, right? So with this we get now to the Friedman equations, where the first Friedman equation, so it tells us how the left-hand side evolves. Left-hand side, the only time-dependent part is that we have is the scale factor. A dot over A is what we call the Hubble parameter. And then on the right-hand side, if we just evaluate this under these assumptions, what we get is 1/3 rho minus k over A squared. And this is what I will refer to as the first Friedman equation. And then the second Friedman equation is an equation for the second derivative of A. So this then corresponds to h dot plus h squared. And this is -1/6 rho plus 3p. This is the second Friedman equation. Now what we can do is to see, we'd maybe like to also know how the energy density actually evolves. So to do that, we can take the derivative of this first equation, which will give us a 2h h dot on the left-hand side. Then we can substitute this h dot using this equation here. And then what we get is what is called the continuity equation, which is that d rho over dt is minus 3h rho plus p. So this tells us kind of that like imagine you have a pressureless substance, right? So p is 0. Okay, that just tells you, okay, the energy density decreases as the universe expands. And then we can rewrite this d over dt as a d over a dA, just using the definition of h here, or in other words, substituting that here h is a dot over a. And then we get that d rho over d ln a. So the motivation for doing that is that often we will not use t as a time variable, but a as a time variable. And then we get minus 3, 1 over omega, which tells us, this is a simple, I should say omega. Omega is a p over rho. This is the equation of state parameter of the universe. And so this tells you, depending on the value of omega, it tells you how the energy density behaves. And in particular, for radiation, we have omega as 1/3, right? As you can see directly here. Thank you. Yeah. So, which also means, right, so then we solve this, right? And we get rho is proportional to a to the minus 3, 1 plus omega. And then for radiation, right, which is 1/3, which we see just by comparing these two here, you see that, okay, as expected, the energy density scales as a to minus 4. So a factor power 3 for the volume and an extra factor for the redshift. For matter, we have omega equals 0, which is just energy density scales as a to minus 3. And for the cosmological constant, we have omega equal minus 1. So I'm kind of absolutely sure you've seen at least this equation before, but I just wanted to show you once explicitly what are exactly the assumptions that we need to get to this point, so that then later during inflation we'll kind of see what we need to modify. And so just for reference, this is what we'll have then on the slides. Okay. So now with this information, well, let me leave this up in case you still need it. Okay, so now with just this basic information, we can already determine a couple of very basic observations in the early universe. So if we look at how the energy density evolves as a function of the scale factor, we saw that for the radiation energy density, right, we have something that goes as a to the minus 4. For the matter, we had something that goes as a to the minus 3. And for the CC, we had something that was constant. Right, so this is rho CC. Which means that in different epochs of the universe, different components had to have dominated, simply by the way they scale. This also means that there's going to be a point in time where we have equality between radiation domination and matter domination, meaning at this point we have the same amount of radiation and matter. And there's also going to be a point down here where the radiations become completely subdominant, but matter and DCC have the same value, AM lambda. And today, we can measure these quantities today I'm just going to give you the numbers now, and then later I'll tell you how we actually measure them. So today, the fraction of energy in the CC is 70%. The fraction in the matter is 30%, roughly. And radiation is basically negligible. And with this information, we can go back and we can compute at what point in times these things happened. So the energy density in matter, we said scales as a cubed, right? Which means it scales as, well, scales 8 to the minus 3, which means it scales as temperature cubed in an adiabatically expanding universe where the entropy density is constant, right? Because we saw that the entropy scales as T3. So the matter energy density is just the energy density of matter today, which is the total energy density today. Let me call that rho 0 times rho matter, the fraction that is in matter, omega matter. And this thing via the first Friedmann equation is 3m Planck squared h0 squared. So it will be sometimes setting m Planck to 1 and sometimes not. So up there I set it to 1. So I normally set it to 1, but sometimes I take it along just to make sure we have the dimensions correct. And then the temperature at when we want to evaluate this versus the temperature today when we measure this guy. And the temperature today is the temperature of the CMB is 2.7 Kelvin, or in electron volts is 2 times 10 to minus 4 eV. Now, the radiation energy density from up there is p squared divided by 30, number of degrees of freedom, t to the 4. And now this number of degrees of freedom has a bit of a subtlety. It obviously depends which stage of the evolution are we in, which particles are actually in the thermal bath. So we want to evaluate this at relatively late times. We'll see when we get the result. In hindsight, we'll see why that makes sense. So the only particles that we'll have in the thermal bath are the photons, which will be 2 bosonic degrees of freedom. However, what we have to put in here is not 2, but we have to put in this factor here. I'll write it down and I'll explain it. Okay, and if we evaluate this, this is larger than 2. So the reason that's going on here is neutrino decoupling. So at some point around the mega electron volt scales, neutrinos decouple. And so we do still have a radiation component which is in neutrinos, but it's decoupled from the plasma, where it's decoupled from the photons. And hence, so the 7/8 is just for the factor we need for the fermions. 6 is 3 neutrino species times 2 degrees of freedom for each Weil fermion. And this 4/11 is the effective, the factor between the effective photon temperature and the effective neutrino temperature. Because after neutrinos decouple, electrons and positrons decay into photons. And hence the temperature in the photon bath is different than the temperature in the neutrino bath. And this 4/11 is simply the number of degrees of freedom with the neutrinos versus the number of degree of freedoms without the neutrinos. So this is the effective reheating which goes into only into the photons, but not the neutrinos, because the neutrinos have already decoupled. Okay. So with that, we can now determine all these points. So if you want to get this guy, we just have to say, okay, when is matter equal radiation? We just equate these two equations, and we get something like that the temperature at which this happens is something like 5.68 omega matter, h, which is the dimensionless parameter for the Hubble constant, which comes from here. And if you evaluate that, that's something around the electron volt scale. So this is this guy, and for the other guy, we need to set rho m is rho lambda, right? We just equate this guy with this guy, and we get a temperature of 3.5 Kelvin, which is 3 times 10 to minus 4 electron volts. So what does this tell us? So we see this temperature here is very close to the CMB temperature today. So this crossover happened on cosmological timescales extremely recently, right? So it's clear from just the way the things scale, it's clear that the CC had to, if present, the CC had to dominate at some point, but that it dominates just now on cosmological timescales is a coincidence to our current knowledge, but it is a coincidence that people wonder about why that is the case. Then here the decoupling between matter and radiation happened around the electron volt scale, which now that we have the results also explains why I was only talking about neutrinos and photons, and because everything else at the electron volt scale is already massive and already decoupled from the thermal plasma. Are there any questions so far? Yes?
This equation for radiation density is valid only when we can consider neutrino relativistic, right?
Yes, exactly. I'm assuming to do this, right, so that I put a 6 here and not a 4 or a 2, I'm assuming all neutrinos to be relativistic. Yeah.
Can you write a little bit larger?
Okay, I'll try.
Can you write a little bit larger? Thanks.
Yes, thank you. Okay, so that's kind of the cosmology 101 that we need, right? And now we get to some actually interesting physics, which is the CMB. So let me first erase my small writing. Okay, so to talk about the decoupling of the CMB, we need to understand more precisely what's going on at the universe at the EV scale, which is very close to matter radiation equality, which is again a bit of a coincidence, right? But this is once we go through this, you'll see why this is the scale we need to talk about. So what are the degrees of freedom that we have at this point? We will have neutrinos, we will have photons, we will still have electrons, we will have baryons, we will have the CC, and we might have dark matter. Well, let's assume we have dark matter. And we will have metric perturbations. And everybody talks to the metric. All the other particles of the standard models are unstable, have already completely decayed, become irrelevant at this point. So the entire matter sector that we have is this, right? So we have electrons, baryons, dark matter. Electrons are non-relativistic at this point. So these guys are going to be radiation. Again, I'm assuming the neutrinos will be relativistic here, but at EV, that's a pretty safe bet. And then we have these guys, the electrons and the baryons. They are tightly coupled through Coulomb scattering, meaning I can really consider them as a tightly coupled plasma with these two constituents. So I can, to very good approximation, I just can describe this as basically one fluid component with some properties. And here, the photons with the electrons, they are coupled through Thomson scattering. which is going to be the process of relevance for the CMB decoupling. So this is basically an electron interacting with a photon in this way. And the process of interest is now going to be that at temperatures of about 0.3 electron volts, this is the binding energy of hydrogen. And at this energy, the free electrons and the protons combine into neutral hydrogen, which means that Thomson scattering very rapidly becomes completely inefficient. And it's basically the freeze out of this Thomson scattering process, which means, to be careful I don't fall down here, which means that from basically as the universe cools down, Thomson scattering rapidly becomes inefficient because the number of free electrons goes down, and hence the photons can free stream, and that's going to be the source of the CMB light, of the cosmic microwave background. So this is what we had so far, and now at this recombination temperature, as I said, right, the electrons and the protons combine into neutral hydrogen, which means the Thomson scattering become inefficient, the photons free stream, and that predicts that there will be a black body radiation. Black body because initially it was a thermal plasma, and then very rapidly Thomson scattering went out of equilibrium. So we predict a black body spectrum which had the temperature of 0.3 electron volt at the time when it was emitted, and then it just gets redshifted. So we predict a black body spectrum with a temperature which is shifted just by the ratio of the scale factors between today and recombination, which is just the ratio of the equivalent to just the ratio of the temperatures between today and recombination, which we just computed. And that black body radiation we should see today. Now, when we computed the temperature for matter radiation equality, right? I told you already something about the energy densities, the ratio of the energy densities of the universe today. Now, initially, when this computation was done, this was not known, right? So one just had the prediction there should be black body radiation. It should be redshifted by this factor, but one didn't know how to compute this factor because one didn't know what are the ratios of the energy densities in the universe today. So one did not know where exactly to expect, at which temperature expect this black body radiation. But then there was kind of a bit of a coincidence that there was people working, Penzias and Wilson, working on radio astronomy. Well, no, not radio astronomy, radio telescope. They were trying to do a communication, working for telecommunication, and they nearly accidentally discovered precisely this black body radiation, and that is kind of one of the key predictions of the expanding universe, of the Big Bang theory, because that at the time was really kind of what decided the game between following the paradigm of the Big Bang theory or following the paradigm of the static universe. And okay, today we've measured it at that temperature. We've also measured it very well by now, and we know it's extremely homogeneous. Now, in order to completely predict the physics of the BBN, what one needs to know, right, is okay. One needs to know the different energy components today, so that one can correct this redshift factor, or vice versa by measuring the redshift factor, right? One can deduce the ratio of the energy components today. But in order to even describe the CMB even more precisely, and you'll hear much more about that in Fabio's lectures, is you need to be able to describe this plasma here and the properties of this plasma. So in particular, if you vary the relative importance of any of these components, you will change the properties of the plasma, and that will impact exactly how Thomson scattering freezes out, and it will impact how exactly you see the CMB today. And this is why the CMB is really a probe of all the things that were important at the time of rescattering. So even radiation energy density, which is completely negligible today, at the time of the CMB it mattered very much, right? Because it's matter radiation equality that we're looking at there. And so the CMB is really an amazing tool to not only measure the total expansion history of the universe, but also to measure all the relative importance of these different components. What one can also measure, and we'll get back to that in the last 2 lectures, is we're talking here about the properties of some fluid. And as you might know, right, these fluid undergo some oscillations. And kind of the properties of these oscillations are determined by these parameters here. But the initial conditions for these oscillations, the initial seeds to kind of perturb this fluid, this is something which comes from inflation, and this is what we'll get back to in the last 2 lectures. Okay, any questions on this? Yeah.
Just to clarify one thing, Valerie, you said that at 0.3 electron volts you have this decoupling of the recombination.
Yeah.
Because that was roughly the binding energy of hydrogen.
Yeah.
However, the fundamental state of hydrogen is 13.6 electron volts, which is significantly higher than the 0.3.
Yeah, yeah, and that is because one really has to look. What one has to do is one really has to look into the cross section for Thomson scattering, right? And in the cross section for Thomson scattering enters the electron density, and so then you kind of get a Boltzmann equation for the electron density. And it really matters kind of when that electron density falls below the threshold, such that the condition that we really need is that the scattering rate, the Thomson scattering rate, has to become smaller than the Hubble expansion rate, right? And that's the actual condition when this freezes out.
The high photon entropy had to do with that. But in reality, is this a factor? Like the fact that you have 10 to the 8 or 10 to the 9 photons per baryon, does it really influence this?
It does influence a bit. We'll see it, I think, in a second when we do BBN. The effect is much more pronounced, and we'll see exactly that effect.
Okay. But not so much here, right?
Not as extreme as in BBN.
Okay.
In BBN, it really matters a lot.
More questions?
Okay. I don't think I was really writing bigger, right? But I'll try again on the next blackboard. Okay, you can think while I wipe the board. Okay. Since I have slides, I decided I could put some pictures, right? So you see Penzias and Wilson with their famous telescope that discovered the CMB. You see this is the beautiful black body spectrum as measured by COBE, the first satellite experiment dedicated to this. And this tail is what Penzias and Wilson saw. And then this is the COBE satellite, the Planck satellite, and what you see here is the map of the anisotropies, right? So I told you this is very isotropic to about 1 in 10 to the 5, and this is the sky map if you show the tiny temperature fluctuations. And this is where you get all the physics on really all these different parameters. And this curve is where you get the this temperature ratio from. Okay. So then the last topic for today, let's talk about BBN. So Big Bang nucleosynthesis, which means the formation of light elements. Okay, we need to go through 3 steps to understand BBN. The first step that we need to go through is neutron freeze-out. So at temperatures much above the MeV scale, neutrons and protons are frequently interacting. So you can, for example, have a neutron plus an electron neutrino going into a proton and an electron, and so on, right? You can have similar interactions all mediated by the weak force, flipping things from one side to the other. And the rate for these interactions is if you go from a proton through a neutron, that's going to be slightly more difficult than going from a neutron to a proton, because there's a mass splitting where this delta m here is the neutron mass minus the proton mass, which is about 1.3 MeV. Okay, so because the neutron is slightly heavier, the neutron wants to decay to the proton and not the other way around. But if you're at very high temperatures, that doesn't matter because you have plenty of energy in the bath and you can easily go in both directions. So from this, if we define the fraction of neutrons, so the number density of neutrons divided by number density of neutrons plus protons, we can write down a Boltzmann equation for the amount of neutrons. So the amount of neutrons, or the fraction of neutrons, will be sourced by protons decaying into neutrons. But then, of course, we also have the neutrons decaying. And you will have a similar equation for the protons, but we don't care about the protons because protons are stable. They will survive. We need to know the number of neutrons. So just to explain, the reason I'm worrying in the first place about the number of neutrons is that I want to, in the early universe, right, initially, like if everything just cooled down, right, at some point neutrons would decay into protons, and we would, because that's the only stable particle, and we'd be left just with protons and electrons, which means we could only build hydrogen and nothing else. So we need to somehow capture the neutrons into heavier elements before they decay away. And exactly the way we do that will determine how many light elements, well, with light elements, I mean everything heavier than hydrogen, right, but not too heavy. So in order to create these elements, we need neutrons. And so how exactly we create them will determine exactly the ratio of these elements. So this is why I care about the amount of neutrons. And so now we have the Boltzmann equations for the fraction of neutrons. We can look for an equilibrium solution, right? Meaning if we're at high temperatures where this interaction is very efficient, meaning we're above the mass splitting, right? Then this will be, neutrons will be in equilibrium, which means x and dot equals 0, right? That's the definition of equilibrium. And then we can solve this, just the right-hand side, right, by plugging in this here for the proton to neutron ratio, and we get that the equilibrium solution for neutrons is 1 plus e to the delta m over t to the minus 1. Okay, so the bigger the mass ratio, the more suppressed the neutron fraction is in equilibrium. Now, at some point, this reaction freezes out. And the freeze out of this reaction happens when the weak force, which is mediating this, simply cannot compete with the Hubble expansion anymore. So when these rates here, lambda np and lambda pn, become comparable with Hubble, so really this is comparing the weak force with gravity, then this reaction decouples. And the temperature at which this happens, so I'm calling this again decoupling, but this is not CMB decoupling, right? Now this is now decoupling of this rate. This happens around MeV. And that is, as we'll see in a moment, very luckily, this number is very close to this number, right? Despite that this here, the mass splitting between neutrons and protons has something to do with QCD and how kind of I actually generate masses for my confined particles from my elementary particles. And this is something to do with how the weak force talks to gravity, right? So there's completely different physics, but by pure coincidence, the number is similar. So that means that at this temperature, the neutrinos decouple, and that means that their fraction freezes out at the rate that it has at that time, right? So we get the neutrinos at decoupling time is just the neutrinos at equilibrium at decoupling time, and it's exactly that. And now you see, luckily this thing is order 1, right? Because it's basically that number divided by that number. If that were not the case, in particular if the decoupling temperature, like if this mass splitting were much bigger, then simply there would be no neutrons left when this rate freezes out. Okay, so this is kind of the first BBN miracle, is that we actually, at the time when the neutrons freeze out, or when this interaction rate, not neutrons, when the neutrons freeze out at this decoupling temperature, that we actually still have in equilibrium a significant amount of them left. Okay, now the second point that we need, so this was A, B, is, well, let me wipe the board again. The second point that we need is now we need to form deuterium. And now we get back to your point. So we have some neutrons left. And now we want these neutrons to bind together with protons to form deuterium. And we need a photon here. So this interaction is actually in equilibrium until very low temperatures, right? So remember, we're now at MeV scale. This interaction is in equilibrium much, much longer, until like the milli-electron scale. So we have another 6 orders of magnitude until this reaction freezes out. So we cannot wait for the freeze out of this reaction, right? We need to work with it when it's in equilibrium. And in equilibrium, we can use just the Maxwell-Boltzmann formula to get the fraction of deuterium. So again, this is the number density of deuterium with respect to the number density of all massive particles at that time. So it will depend on the number densities on the left-hand side. There's some numerical prefactor. We have the temperature divided by the proton mass. We have eta, which I will explain in a second. And we have e to the delta d over t, where delta d, this is again the mass splitting, which is relevant for this equation. So in this case, this is the neutron mass plus the proton mass minus the deuterium mass. And the eta accounts for these gammas here. And the eta is the baryon number density divided by the photon number density, which is about 10 to minus 10. I'm going to tell you now that it's 10 to minus 10. Actually, the fact that it's 10 to the minus 10 is something that precisely we can read out of the result from this calculation, right? Because we'll get numbers, and these numbers will very sensitively depend on this. And we only get the right numbers when we actually put 10 to minus 10 and not something else here. We'll see that in a second. And so now this is exactly what's happening. What's happening is exactly your point, that here we have a lot of photons on the right-hand side, which is why kind of there's a pressure to have the reaction running in that direction, not the other direction. Basically, the photons want to always dissociate the deuterium, and hence the fraction of the deuterium fraction is strongly suppressed by this right here. And that means that if we actually want to have a significant fraction of the neutrons in deuterium, so if we want to have the deuterium compared to neutrons and protons of about order 1, we have to wait. We have to basically wait until kind of really enough photons are depleted, or simply expanded away, that really this fraction really becomes large, because initially at the MeV scale, where you'd think this is an equilibrium, you think this would just happen immediately, right? But it doesn't happen immediately because of all the photons. This is what is referred to as the deuterium bottleneck. And so if we want to actually reach an order 1 fraction here, we have to wait until a temperature, which I will call TBBN, which is actually a factor 30 smaller than what you would naively expect. So a factor 30 smaller than just this mass ratio there, or this mass difference there. And it's about 0.068 MeV, right? Which is noticeably smaller than this 1.3 MeV that we had in the previous step. And now, again, luckily, okay, so this temperature corresponds to a time measured from the beginning of the universe, which is about 3 minutes. And now, very, very luckily, and this is the second kind of magic coincidence in BBN, the lifetime for neutrons is 15 minutes. Which means that despite that we're stuck here, in the previous step, we had the freeze out of the neutrons at a sizable abundance. Now, however, we had to wait in order to kind of safely bind them into our deuterium. And very luckily, while they were waiting, they didn't decay yet. But not by much, right? Really not by much, right? Given the scales that we're talking about. So this is kind of the second magic coincidence of BBN, that there's actually the neutrons decay just slow enough that they're still around when we actually manage to form a significant amount of deuterium. Okay, and then the last point is we need to now actually get we need to get the light elements. So we have deuterium now, but only deuterium. But that was the most difficult part, right? Because that had this photodissociation part. Now we can, for example, take a proton and a deuterium, and we can form helium, and so on, right? I mean, that was kind of the difficult part. So we can now form helium, we can form tritium, we can form 4 helium, but then we stop, because there's no stable nuclei with A equal 5. Which means that what this process is doing, it's basically taking all the deuterium that we have, and it's converting it into helium-4. And then we get stuck, because then we have no A equal 5 nuclei. But that means that we can, from the deuterium fraction that we computed here, I should give you a number. So this is, okay, I should have given you a number for the neutron fraction. So when we computed the neutron fraction at T decoupling and equilibrium, that was about 0.15, because that's the number we need now. Because, okay, so now we convert all our deuterium into helium-4, which means that the helium-4 fraction, so the fraction in helium-4 is just twice the fraction in neutrons at the time of decoupling, because basically nothing happened since then. And so, no, sorry. The time of the neutrons at the time of the neutron fraction at this temperature here, which is compared to the time of decoupling, just suppressed by the neutron decay. So e to the minus TBBN divided by tau neutron, which, as we said, luckily this is not too big of a number. And then we just plug in the different masses. We plug in this number here, and we get a helium fraction of about 0.24. Yeah, and this, I recall, right, this kind of relatively sensitively depended on this eta, because this eta determined this time here, which enters in the exponential here. So, as we said, right, the small eta delays the helium-4 formation. And hence the helium-4 is really a measure of eta. And I just did helium-4 now, but you can do, and because then we can have a bit of a blockage, right, because then we hit the A=5 gap. But you can continue this process, and you can look at lithium, you can look at deuterium, and you can also, again, you can compute, basically by hand, you can compute the abundances, just from this very basic physics. And then this is what you get. So this is from the particle physics data group. So what you see here is, on the axis, you have eta. Here you have the helium-4. This is the one we discussed. Here you have similar plots for lithium and for helium-3. And this band is what we just computed. This is the prediction of helium-4 as a function of eta. And I told you, no, we'll take eta 10 to minus 10, right, which is exactly in this range here, of course. And this box is the directly observed helium-4 value, right? So when you try to observe helium-4, of course, you have to be a bit careful, because not all helium-4 that we see is primordial. Also, like star formation happened and so on, right? But you can go to parts of the universe where things are still relatively pristine, and you can measure this helium-4 fraction. And then from this prediction and this helium-4 observation, you can then predict, or measure, if you want, you can measure eta. But then you can do the same exercise with the other elements, right? And you need to get the same value of eta. There's only one value of eta, right? So the fact that this works, so the fact that basically all the observed values, so this observed value, and this observed value are roughly pointing to the same value is already good. You can see that we do have a lithium problem here, right? Lithium is preferring a somewhat smaller value than the others. So that is an open question. And then what you see in this vertical band here is the CMB measurement, right? Because I told you also the CMB is sensitive, very sensitive actually to the amount of photons present, and this is nothing else what this guy is measuring, right? The baryon to photon ratio. And this is the measurement by the CMB, and you see that it matches very well with at least the measurements from the helium-4 and the helium-3. And this is one of the reasons. This is why BBN and CMB are kind of one of the key ways to measure the key components of the early universe. Okay, I stop here.
Thank you,
Questions for Valerie? There you go, Marcus. Thank you very much for the lecture. So it's about this figure, actually. Like you mentioned that from here you can see that the CMB actually agrees very well with predictions, but I don't know how to read this this graph.
Okay.
Because you have like complete degeneracy on the vertical axis. I really don't know. Sorry.
Okay. So let's just look at helium-4, right? So what we just computed is this purple line here. We computed helium-4 as a function of eta. Right, if I go back, here, right, we computed the deuterium abundance, which in the end then determines the helium-4 abundance as a function of eta, right? So let's say, and I told you, okay, let's put eta 10 to minus 10, and then we got a fraction of 0.24 for helium. Let's say we don't know what is eta, right? Then we just have this function as a function of eta, and that function is this line here, okay? Now we make an observation, right? And we observe what is actually, how much helium-4 do we have in our universe. And we get about 0.25, right? As indicated by this yellow box. Would be a yellow line, right? So from that, we would now read off that eta has to be between this value and this value. And now the CMB also makes a measurement of eta. But that measurement does not at all depend on helium-4 or lithium or anything, right? It just gives you a measurement of eta, and this measurement of eta is here, right? So it's at whatever, 2, 3, 4, 5, 6 times 10 to minus 10. And now, when I'm saying that there's agreement, what I'm saying is that this value of 6 times 10 to minus 10 falls within this window here. And hence there's agreement between the two. But down here, you see there's a bit of a discrepancy, right? This is the 2 sigma from the CMB, and you see the yellow box prefers over here.
So the yellow box is 2 sigma or 1 sigma? Do you know?
Honestly, I don't know.
More questions for Valerie.
So it's about this BBN magic that you talked about earlier, which in fact is a balance between the weak, the strong, and also the electromagnetic, right?
And gravity.
And gravity, right? Yeah, but I was referring to the mass difference of the proton and the neutron, and because the contribution is not only strong but also.
So this miracle here.
Yeah,
Yeah.
the 1.293 is a combination of
Yeah.
strong plus the electromagnetic contribution to the
Yeah.
Mass to the proton, right?
Yeah.
And it's also the liquid
Yeah.
balance. Yeah. So it looks like a lot of magic coming, going around, in quotes. And I was wondering if there is anthropic or multiverse type of thing, or
Yeah.
along this line. And
Yeah. I mean, yeah, definitely, right? So yeah, right. So the thought is, okay, if this mass splitting were a bit larger, right, then basically we would not have. Then when the neutrons freeze out, there would be very, very little neutrons, right? Which means we would live in a universe which doesn't have any light elements, which means we just have hydrogen, right? And then the logic is, okay, well, but we cannot live in a universe which has just hydrogen. And in particular, the logic is that, okay, nobody can live in a universe which is just hydrogen. So the fact that we are kind of conscient beings and we can ask ourselves this question indicates that kind of we have to be at least on the one side of that bound, right? And then these anthropic arguments do have the tendencies to sometimes push you close to that bound, right? But I mean, a priori, you could still be. I mean, we could have much more neutrons, right? And I don't think there's anything wrong with a universe that has much more neutrons than we do.
And the lifetime, I mean, because also the lifetime depends upon, the mass difference and the weak interaction.
So you're asking if this is two separate miracles or if this is a single miracle?
Just to, it's
Yeah.
Monday, to start.
Yeah, I mean, definitely there's some related physics going in, right?
Yeah,
of
yeah.
course, right? I mean, it's not completely. I mean, also, of course, this decoupling is not completely unrelated with the mass difference, right? I mean, if this mass difference were very big, then you would have two rates and they would decouple at simply different temperatures, right? But okay, the fact that they kind of decouple at the level where you still have enough neutrons, right? As you say, a lot of things enters there, right? Because you have the QCD, you have the electromagnetic, right? You have the weak, and you have gravity, right? And of course, some of these obviously enter into the neutron lifetime again, right? In particular, the weak force, but not exactly in the same way, right?
Yeah, and the mass difference as well, because it's phase-space. No?
Yeah.
Anyway, so.
And there you have the different. I mean, then you have this mass difference, right? Which is again a different mass difference.
Yeah.
But just to say, I think we're extremely lucky that we're living in a universe which is very close to this boundary, because otherwise I think we would have a much more difficult time to do cosmology, because the fact that we're kind of in a universe which kind of exponentially depends on all these parameters means we can actually measure them today. Otherwise we could not, right? I mean, if we were kind of very well away from these boundaries, it would be very difficult from today's measurements to say anything meaningful about the primordial abundance. So maybe the fact that we're cosmologists has an anthropic influence here.
Thank you for the talk. I wanted to ask, what are the effects that can be caused by new physics beyond the standard model on these predictions? I know that new particles, they can inject high energetic neutrinos and change the predictions, or they can inject mesons that would interact drastically with neutrons and protons. Maybe you can tell about other effects.
Right. So one I mean, this is the only lecture I was going to talk about standard model physics, right? But yeah, so one thing, for example, is that here, all the time, like when we compute these equilibrium number densities, all the time I've assumed that there are no chemical potentials in the early universe, right? In particular, I assumed that there's no chemical potentials for electrons and for neutrinos. If you had chemical potentials in the sense that you had an imbalance, significant imbalance between, say, neutrinos and antineutrinos, which is something that is basically unconstrained by observation. We know the baryon asymmetry, we know. The lepton asymmetry, we don't know, basically. So you could have a huge asymmetry, order 1 asymmetry between neutrinos and antineutrinos, and we wouldn't know. But that would impact these reaction rates, right? Because here you have a neutrino and not an antineutrino, right? So it matters. So if you had a different number of neutrinos or antineutrinos, you would change kind of the neutron to proton fraction, and that would impact the observations of BBN. And actually, there is currently a new measurement, helium-4 measurement, by the Empress collaboration, which is slightly off this preferred CMB value. And then many things can go wrong, right? Because I said, when you measure helium-4 today, you have to be very careful that you actually measure the primordial helium-4 and not some secondary helium-4 that was produced, right? But one explanation for this current anomaly, which is 3 sigma or something, right, is that maybe indeed there was a lepton asymmetry in the early universe, and that would kind of shift all of these values a little bit, to give you one example.
Yes, and another quick question: what is the status with lithium problem? Like,
it's still a problem. It's still, I mean, it's not a huge problem, right? I mean, it's, you know, within 3 sigma also everything is okay, right? There are proposals, right? But I think nothing really has happened. Well, nothing that I'm aware of has really significantly happened. We have this problem since basically we have WMAP, right? And it's not getting any better.
thank you.
Yep.
Yeah.
No,
Okay, there it goes. Okay, very good. All right, so I was asked to come here and tell you about dark matter, although looking through last week's lectures, it looks like you've already heard quite a bit about dark matter. So thanks very much for the organizers to the invitation. I'm very happy to be here. So over the next 4 lectures, we may recover a little bit of ground that you've already covered in the last week. I figure if it's important, it won't hurt you to hear it twice. So today, I want to begin by by just talking, I want to start out, especially since it's Monday morning, by giving a little bit of a historical overview of the evidence we have for dark matter and what we think we know about its properties as a result of that evidence. Then I want to say a little bit about the big picture of how we think about this puzzle of dark matter, about ways that we might classify dark matter scenarios and ways that we might go after them. And then towards the end of this first lecture, I want to talk about the standard thermal freeze-out paradigm, which I think has been at least mentioned before in the lectures last week. I want to give you my take on it and expand on it a bit, because I'm going to use this because this is not the only way that you can get the right amount of dark matter in the universe, but it is a very common benchmark for a large number of searches. And so I want to use that in our second lecture as we talk about benchmark models for dark matter, the possible parameter space for dark matter, and the kinds of effects that non-trivial dark matter physics could have in the late universe. So we'll do that later today. I want to talk about the features of cosmological history for particle dark matter, especially thermal relics. Today's going to be focused more on cosmological bounds and the theoretical space of possible dark matter models. Tomorrow, I'm going to go on and talk about our current searches and constraints on dark matter scenarios. Now, Francesca Calore will be coming later this week and focusing on astrophysical and cosmological searches for dark matter and for other new physics. So I'm going to leave indirect detection later to her, and my lectures tomorrow will focus primarily on terrestrial searches, indirect detection and accelerators, and in dedicated experiments to look for wave dark matter. Now, unlike Valerie, I put all my equations on the slides. I'll try to go through those slides fairly slowly. Please feel free to raise your hand and stop me and ask questions as I go. And I can always write on the blackboard if you need more detail or want me to fill in steps from the slides, okay? And please feel free to ask questions as we go. All right, so let's begin with a bit of a historical overview of the dark matter puzzle. So going back to the 1920s and 1930s, various astronomers and cosmologists were trying to estimate properties of the universe that was becoming visible to them. And in particular, Zwicky in the early 1930s was the one who coined the term dark matter to explain some puzzles that he was seeing in the observations of galaxy clusters. So he was looking at the Coma cluster and wanted to measure the mass of this cluster, and being a good scientist, he was like, all right, let me come up with two different methods to measure the mass of this cluster and see how self-consistent they are. So the first method was essentially a counting method. It was to say, all right, we want to try to estimate the mass from the mass to light ratio calibrated to local galaxies. So he just counted the number of visible galaxies in the Coma cluster, added up the total luminosity, and then used a mass to light ratio estimate from a local stellar system, the Kapteyn stellar system, and got a mass estimate from that. So this works on the assumption that there's a simple ratio between mass and luminosity that you can calibrate in local systems and that extrapolates well to galaxy clusters. The other method was to say, all right, gravity depends on mass. Great. So let's look at how fast the particles are moving. That will tell how fast the galaxies within the galaxy cluster are moving. That will tell us something about the gravitational potential that they're moving in. So using the virial theorem, this relates the kinetic energy of the galaxies in the cluster to their potential energy in the gravitational potential provided by all the mass of the cluster, presumably at this time from the galaxies. He estimated the velocities of the galaxies using Doppler shift observations. From that, inferred the potential energy of the cluster, and from that, inferred its mass. Now, the problem is that when you do these two mass estimates, these numbers are different by a couple of orders of magnitude, with the second one being larger. So this could have a number of different causes, but one that Zwicky advanced in this paper was, maybe the reason this luminosity-based assumption is low because there's a lot of non-luminous matter in the system that is nonetheless contributing to the gravitational potential. At this point, he was probably not thinking about QCD axions or new physics. He was thinking about things like old burnt-out stars that weren't radiating in the frequencies that he could look at. But he called this dark matter, Dunque Materie. So that was, some evidence that maybe there was something going on beyond the luminous matter in the universe that we didn't understand. But the point at which this became formulated as a well-defined dark matter problem was some years later in the 1970s and in the 1980s when a number of people, including most famously Vera Rubin, started to look at the rotation curves around galaxies. So this was looking at stars and gas clouds orbiting around galaxies, and this is the same idea as Wiki's second method. You can look how fast tracer particles, aka stars and gas clouds, are moving and use that as a probe of the gravitational potential. And here are some results from Rubin, Ford, and Thonard in 1980, showing ensembles showing for a large number of galaxies how the velocity in the plane of the galaxy of these tracers behaved as a function of distance from the center of the galaxy. And this plot on the right is showing what you would naively expect if you had a contribution just from the bright, luminous, visible disk of the galaxy that they would see. Then you would expect these rotation curves to fall off, as shown by this curve. Now, and you can do sort of the math of this rather simply. If you say, okay, if you said most of the mass of the galaxy is enclosed in a rather compact region at the center, you would say, all right, our centripetal acceleration, v squared over r, is equal to gm over r squared. So then we would expect the velocity of that circular motion to fall off as 1 over square root r. But instead what you see is something more like this, points that the rotation curves remain flat with distance from the galactic center, at least out to some significantly larger radius than the visible matter of the galaxy. So for that, you need a halo of matter surrounding the visible matter such that the enclosed mass scales up with r. So this could mean a couple of things. It could mean maybe our Newtonian gravity that we are using here is a bad approximation to gravity on the scale of galaxies. Or maybe we're talking about some new unseen matter component that makes up this extended halo. Now, so in that case, that would tell us this matter component needs to extend to much larger radii than the observed galactic disk. So you might ask, okay, these both seem like reasonable possible assumptions. There were two pieces of evidence that, as far as I can tell, have meant that much more of the field thinks about dark matter as opposed to modified gravity to explain these particular observations. One of them you've heard a lot about already, which is the CMB. The other one was this famous study of the bullet cluster by Clow et al. In 2006. So the idea here is if you're trying to tell the difference between extra matter and modified gravity due to the baryonic matter, it's going to be pretty hard to tell those apart in equilibrium systems, just because the dark matter is gravitationally attracted to the baryonic matter. If you've given the systems a long time to equilibrate, wherever the dark matter is, there will also be baryonic matter and vice versa. So it's going to be a bit hard to tell the difference between a modified effect of baryonic matter and just of dark matter. But you can avoid this by looking at non-equilibrium systems that have not yet had time to relax to an equilibrium configuration. And in particular, you can look at systems of colliding galaxy clusters. So this is an image of the bullet cluster in X-rays. This is a region where two galaxy clusters have collided with each other. They've slammed into each other. The gas clouds associated with the two colliding clusters have run into each other, exerted pressure on each other, heated each other up, and that's why they're shining in X-rays. But that pressure should also cause those gas clouds to slow down due to the drag forces. Whereas if there were halos of some additional matter associated with these galaxy clusters, and that matter had significantly different, significantly smaller interactions to the visible matter, you might expect those halos to just pass through each other and keep going. And that is consistent with what we observe. So the green contour lines on this plot are showing a reconstruction of where the mass in this system is as measured by weak gravitational lensing. And what you see in this lower panel is that there's actually a pretty substantial displacement between the visible gas, which is thought to hold most of the luminous mass of the cluster, and the reconstructed mass distribution. So this is somewhat hard to explain just by a modification of gravity. You can think of things that would change how gravity falls off as a function of distance from the centers of these regions, but it's a little hard to see why the region with the strongest gravity would be actually displaced from where the visible matter is if the only thing that's around is visible matter. So that's one of the key elements in favor of there's some kind of component, and furthermore, it needs to have different interactions than visible matter. Now, you might still ask, okay, so if there is this new matter out there, what are we talking about? And one key question is, are we looking at some kind of new particle dark matter, or are we looking at some kind of compact objects? Could you be looking at, brown dwarfs or tiny black holes? Such compact objects could be, if they're electrically neutral, which they will become so dynamically, it could be effectively collisionless. Stars are actually effectively collisionless once they're formed. These probably exist to some degree. So the question is, can they be most or all of the dark matter? Now, the CMB results, which you've heard about and which I'll come to again in another slide or two, tell us that the dark matter has to have already been around when the universe was only a few 100,000 years old, which lets out most stars. But the dark matter could be primordial black holes. I'm just going to talk about this briefly. I believe Professor Francesca Calore is going to talk in more detail about primordial black holes in her lectures, but I'll just say a little about it now. So the usual picture for primordial black holes is that they're formed during inflation, which Valerie is going to talk more about over the next couple of days. Although there have been some very recent studies, like just in the last few weeks, suggesting that the usual perturbative treatment during inflation may not be quite sufficient to capture what happens when you have primordial black holes formed. The idea is just that you have an enhancement of power at some scales that allows collapse of very high density perturbations in the early universe into primordial black holes. There are also scenarios where the primordial black holes get formed at a later time in the universe's history. For example, if there's a first order phase transition, the inhomogeneity in that phase transition can also induce primordial black holes. But if we don't worry so much about where they came from and just ask, would we see them if they were the dark matter in the present day universe, then there is a window in which these seem to be a viable dark matter candidate. So this is a review from Carr et al. From a couple of years ago. This y-axis here is showing the fraction of the dark matter that could potentially be in primordial black holes. The x-axis is showing the mass of those primordial black holes in grams on the lower axis and in solar masses on the top axis. And so if we, at sufficiently low masses, between about 10 to the 17 grams, these black holes would evaporate rapidly enough that we should have seen the Hawking radiation already in X-rays and gamma rays. And then at higher masses above about 10 to the 23 grams, there's an ensemble of constraints from stellar dynamics. I believe Professor Bloom talked to you a bit about that last week, and from gravitational lensing searches. So each of these colored lines is an exclusion that rules out primordial black holes making above a certain fraction of the dark matter, and this dashed line across is 100% of the dark matter. The dashed lines are cases where a constraint was claimed, but at least in the opinion of this author, those constraints were not reliable or have been refuted. And so what you see here is that we actually have really strong constraints from gravitational lensing and through dynamics arguments for mass scales from about 10 to the 23 grams all the way up to the mass scale of galaxies. So primordial black holes could absolutely be out there. It's hard for them to be 100% of the dark matter, unless they're in this at least tentatively allowed region, which is about 6 orders of magnitude wide between 10 to the 17 and 10 to the 23 grams. So MACHO's massive compact halo objects in this sense are not completely ruled out. This is an example of a viable candidate where dark matter is not a new particle the way that we would normally think about. It is a compact object left over from the very early universe. These mass scales correspond roughly to the scales of things in the asteroid belt. So we don't know for sure that dark matter is a particle. However, if it was primordial black holes or something similar, it's still true that it would require new physics that we don't currently understand. Just in this case, the new physics would be in their formation. Okay, so we can't completely rule out the possibility that dark matter is some kind of macroscopic compact object. But the other possibility is that it is some kind of new particle, and that's attracted a great deal of attention from the field. And of course, our last big piece of evidence for dark matter, and the one that tells us a lot of important things about its properties, in particular how much of it there is and how long it's been around, is the cosmic microwave background radiation. Now, Valerie just gave a great discussion of the CMB, and you had 4 lectures on the CMB last week, so I'm not going to go into much detail about that. Just recap that when the universe was about 400,000 years old, at about a redshift factor of 1,000, the hydrogen gas became largely neutral, which meant that the universe became largely transparent to microwave photons. The CMB radiation was last scattered at that time. We can measure it now. We can get a snapshot of the universe in its very early history. And that snapshot requires dark matter, or more precisely, some matter component that feels gravity but does not feel radiation pressure. The CMB oscillations, you can think of them as oscillations in temperature and density from basically the competing forces of radiation pressure and gravity. If I have a high density region, gravity will act as a positive feedback mechanism. More particles will be attracted to that high density region. The density will go up further. But if I'm trying to cram a lot of ionized plasma into a small region, radiation pressure will push it apart and act as a restoring force. The physics of this can actually just be parameterized as a force-damped harmonic oscillator. So if we have a matter component that feels gravity and doesn't feel radiation pressure, it changes the effective parameters of that harmonic oscillator and modifies the spectrum of anisotropies in the CMB. So this is a little animation that has been killed by the move to PDF of this slide. But you know, if I could change this little bar that is the amount of matter in the universe as I modified it, this power spectrum of CMB anisotropies would change. So yeah, we find that in order to match the data, we can fit it really well with a pretty simple model, but we need a dark matter component that's about 5 times more abundant than the baryonic matter. Okay, so that tells us how much dark matter there is in the universe, and that it was already around when the universe was only 400,000 years old, which, as shown on this little cartoon, is quite a long time before the first stars really started to kick off when the universe was around 100 million years old. So whatever this is, it needs to be primordial. Let me also just comment, I think this was also mentioned briefly last week, but just as a recap. Again, what we mean by dark matter in this case is a matter component, so it has the equation of state of matter, but it feels gravity, but it doesn't feel radiation pressure significantly. So that means that this CMB observation gives you a limit on how much dark matter can possibly interact with the photon baryon fluid. If it interacts too strongly with the photon baryon fluid, it will couple to the radiation pressure. It will not be dark matter for the purposes of the CMB. So if you, this, you can set a limit on this. If you had some non-negligible scattering between the dark matter and baryons, the effect of that is basically to dampen the growth of density fluctuations in the dark matter fluid. The dark matter fluid normally just feels gravity. Its density fluctuations are not suppressed by radiation pressure. If you couple to the baryons, you turn on that kind of suppression. It also modifies the relative velocity of the dark matter and baryon fluids. You know, normally they're not coupled to each other. They can have some significant relative velocity with the only drag being gravitational. If you turn on a non-gravitational drag force, there'll be friction between them. If they have a large relative velocity, that will heat both fluids and modify their velocities. The effects of these, and this was studied in a number of papers, this is one example by Zhou et al. Back in 2018. You can go look at that paper in the references if you want more detail about this. But what that leads to is a suppression of power on small scales and a shift in the acoustic peaks. And this plot is just showing the fractional changes to the CMB temperature power spectrum, and these different ends correspond to different scalings of the scattering rate between dark matter and baryons with the velocity of the particles. So we can look for this signature in the CMB. We haven't seen it. We can set an upper limit on how large this modification is, and thus we can set constraints on the scattering between baryons and dark matter. There's a little loophole in this, which is if 99% of the dark matter interacts only by gravity and 1% has some kind of non-trivial interaction with the standard model, then that's pretty easy to hide because our error bars on the amount of dark matter versus the amount of baryons are at the percent level. So there's a detailed analysis of this done by Kovets et al., which shows that you can basically evade these bounds if significantly less than 1% of the dark matter is scattering. But this provides a framework for what we know about dark matter. This is in some sense, you know, sort of our first indication of dark matter has to behave significantly differently from baryonic matter, and the bullet cluster and the rotation curves are also give evidence of that. And we can set an upper bound on how much it talks to the standard model. Now, tomorrow we'll talk more about direct detection searches, which also constrain this dark matter baryon scattering and test much tinier cross sections than you can in the CMB. But this is sort of a nice starting point. Now, of course, the CMB also maps out initial conditions for cosmic structure formation, and you heard about both large-scale structure and structure on smaller scales, galaxy scales, last time. So after the photons decouple from the baryons at the CMB epoch, the overdensities continue to grow under gravity, eventually collapsing into virialized structures. We form this cosmic web. This is a picture from a simulation. I guess you guys are all experts on dark matter simulations now. And So we can compare the predictions of cosmological perturbation theory to our universe, and at least at large scales, we get pretty good agreement. But you might say, okay, agreement with what? And this gives us another important piece of information about dark matter. The structure formation predictions vary quite markedly according to how fast the dark matter is going, in particular whether it can free stream cosmologically relevant distances during the growth of perturbations. So your extreme cases are either the dark matter is relativistic during the early phase of structure formation, or or in the opposite limit, its free streaming length is effectively 0. If most of the dark matter is hot and relativistic during the early phases of structure formation, then the free streaming of dark matter would basically wipe out all the growing structure on small scales. In this case, what happens is the first structures that form in the universe are really large, comparable to the horizon scale. And then the way that you get smaller scale structure is that those large structures fragment, they break up. So in this case, you predict that the bigger structures form first. This is in fairly strong conflict with what we observe in the cosmos. But I mean, in principle, it could have happened. It's not very observationally consistent with what we see. On the other hand, if most dark matter is cold, so it's non-relativistic and has a small free streaming length throughout the epoch of structure formation, then small clumps of dark matter form first, and then they accrete together to form larger structures, like building a snowball. So the relative ages of galaxies of different sizes and of galaxy clusters tell us that the bulk of the dark matter has to be cold. If dark matter was mostly hot, galaxies would, in some cases galaxies at the scales we need would not actually have formed by the present day, and the history of our universe would look very different. Equivalently, hot dark matter predicts a very different matter power spectrum to what we see, which is not observed. Now, of course, you can be somewhere on the boundary between these two. You can have dark matter that has a significant, but not horizon scale, free streaming length during at least some structure formation. And that gives you warm dark matter, which would put a low mass cutoff into the power spectrum, wiping out structure below some scales. And we can set constraints on where that cutoff could possibly be from observations like those that Professor Kabir Bloom talked about last time. Neutrinos are hot dark matter. They're relativistic during most of structure formation, but for this reason, the neutrinos can't be all the dark matter. Also, we've now set good enough constraints on their mass that we would know independently that they can't be all the dark matter. All right, so this is enough information to tell us. So we've learned from this that dark matter has to be cold, or at least only slightly warm. It needs to be, collisionless to some degree. It can't interact too strongly either with itself, because that would mess up the bullet cluster, or with standard model baryons, because that would mess up the CMB. It can't be neutrinos, because it can't be all neutrinos, because they're too fast moving to be consistent with the structure that we observe. It could be something like primordial black holes, but that will still require some physics that we don't understand going on in the early universe. So the standard model of particle physics has been spectacularly successful, but within our current understanding of it, it doesn't really offer any good particle dark matter candidates. We need something that's stable on cosmological timescales, near collisionless, cold or warm rather than hot. Within the standard model, if we think about the particles, our only stable uncharged particles that we have running around are the neutrinos, and they're not cold enough to be the dark matter. So putting this all together, dark matter is one of the most powerful pieces of evidence for some physics beyond our current understanding of the standard model of particle physics. And everything that we've learned about it so far has come from studying the gravitational effects of dark matter on standard model particles, or from its inferred distribution. So this is the puzzle. So how do we attack it? So there's an enormous range of possibilities for what dark matter could be, and there are several different ways to try to sketch that parameter space. So now I'm going to start talking a bit about theoretical models. Before I go on to that, any questions about the historical overview? Yeah? If you speak loudly, I can repeat the question back to you if there's a mic issue.
Thanks. In this picture of primordial black holes,
Yeah?
I'm not sure, they will be also present in the CMB.
Yep.
To be the source of this structure formation.
Yep, that's right.
Okay.
So yeah, so there is a constraint that just says if the black holes were too individually heavy, maybe they would sort of not count as particles for the purposes of the CMB and the early structure formation. But if you think about these dark matter M-body simulations that we do that get large-scale structure formation right, and you think about the mass of individual dark matter particles in those simulations, that's often like 10 to the 4 or 10 to the 5 solar masses, right? I mean, large-scale structure doesn't, or small or galaxy-scale structure for that matter, doesn't really let us resolve individual dark matter particles that are lighter than about 10 to the 4 or 10 to the 5 solar masses. So the scale that I'm saying is allowed for primordial black holes is between about 10 to the minus 10 and 10 to the minus 15 solar masses. So they're particles from the perspective of structure formation, even though they're not from the perspective of humans. There are some constraints, especially for the higher mass stuff, that even if the dark matter, so primordial black holes are smooth enough to be the dark matter in that sense. There are some constraints, if these things were around during the CMB epoch, matter could accrete onto them during the CMB epoch. They're electrically neutral, but they, of course, have gravitational interactions. There are some constraints on black holes from CMB accretion. They're relevant to black holes that are close to 100% of the dark matter up around the 1 solar mass scale. So yeah, there are some limits. They're not relevant for black holes as tiny as these ones down here.
Okay, thanks.
But yeah, we actually don't know very much about the small scale structure of dark matter, where by small scale we mean anything on scales about 10 to the 5 solar masses or less.
I have another question also related to this. So these bounds, I guess they are, if you assume that all the primordial black holes have the same mass, right?
Yeah, that's right. Good. So this particular plot is looking at, just like a delta function in mass, which is probably not realistic. There's probably some spectrum. There have been some studies, and I think they're cited from this paper, but if not, I can point you to them, which look at the effects of an extended mass spectrum. From what I have seen of those papers, they do not qualitatively change this result. Like, it is still true that you want the bulk of your primordial black holes to be in this allowed window down here if you want them to explain the whole of the dark matter. I mean, but yeah, sure. You probably shouldn't look at this and be like, right, okay, at this mass range, I can't be more than 10 to the minus 2 of the dark matter, so if my model predicts 1.5% of the dark matter, then I'm ruled out, right? Like, if you want to make distinctions at that level, you would have to do the calculation properly for the full spectrum that you have.
Okay, and a related question is that I don't know about the mechanisms of formation of primordial black holes, but do they usually favor more like an extended spectrum or just one mass for the?
So a lot of so I don't have a great. I know that I don't have a great answer to that. I have seen a lot of papers in which people are able to get a relatively sharply peaked spectrum, but I don't know to what degree that is these fall naturally out of the models versus people are deliberately trying to get a sharply peaked spectrum in order to be in this allowed window. But certainly there are a number of existence proofs of models that give you a relatively, that basically that pick out a particular scale and they give you a peak in the spectrum around that scale. Although modulo, as I said, there are these very recent papers that suggest that some of these, there are these two very recent papers, one of which said you can't get primordial black holes from single field inflation because of issues that come in at one loop level. And then there was another paper right around the same time that said, but you can't trust the perturbative expansion at all. So some of those, we'll see how that pans out. This is very recent work. Some of those models may need to be reevaluated, but at least modulo this question of perturbative control, there are existence proofs of models where you get where there's some specific scale that picks out a primordial black hole scale. Okay, one more.
Thank you. I wonder, more or less, all constraints are to fraction of 1%, and there is one, this p lambda or pa, that is go down to 10 to the minus 8. Do you know what this is?
Let me check on that and follow up with you. It's been so that's around the solar mass to 100 solar mass scale. Let me check. I'll tell you after the coffee break.
Yeah. Okay. Thank you.
Okay, so let's get to what particle physicists do when presented with a problem like this. So one way to think about the possibilities for dark matter are to think about what other puzzles of particle physics or what other kinds of new physics could they possibly relate to. So this is taken from a talk by my colleague Tim Tate as part of the snowmass community planning process that we did in the US about 10 years ago. I'll show you some stuff from the more recent snowmass process in the next couple of slides. So I don't want you to, well, in this room people probably actually do understand everything on this plot, but everything within, I usually say when I show this, I don't want you to read every single word on this plot. This is illustrative. Everything within the red region here is a class of scenarios for what dark matter could be. And this is not an exhaustive list of possibilities. So the first point here is just to tell you that we have lots of ideas for what dark matter could potentially be. Everything outside the red line has is a broader topic of physics beyond the standard model that dark matter could potentially connect to. So for example, dark matter could be connected to new symmetries of the universe, such as supersymmetry. It could be connected to extra dimensions of our universe beyond the standard 3+1. It could be related to puzzles of the Higgs sector or the neutrino sector. In the very popular scenario where dark matter is a QCD axion, could solve the outstanding puzzle of the strong CP problem in the standard model strong interactions. In recent years, there's been a lot of interest in models where dark matter is in its own dark sector, in which case it could interact with new forces that the standard model does not feel, in the same way that the standard model has electromagnetism and dark matter, as far as we can tell, does not interact with electromagnetism, in which case dark matter could be just sort of like the tip of the iceberg of a much larger dark sector. So this is one sort of top-down way to think about the possible particle physics scenarios to dark matter, that we have lots of ideas for what physics could be out there beyond the standard model, and many of them admit a stable, long-lived particle that could be a good dark matter candidate. At the same time, the other thing is, so the problem is not that we don't have any ideas for what dark matter could be. We have lots of ideas for what dark matter could be. We'll talk about some more of them. We'll talk about some of them later today. But at the same time, it's true that all of these scenarios are capable of providing dark matter candidates that are consistent with both all the current observational evidence and all the current constraints. So from the data that we have, we don't have a really good way to tell at present which, if any, of these theories are actually true. So another way to think about the dark matter, so this is sort of a top-down way to think about the dark matter problem. What other puzzles could it connect to? Another way to think about the dark matter problem is sort of from the bottom up. Just say, all right, we have this observational statement that there is a component that behaves like dark matter in our universe. What can we say about its properties? So one way that you might try to classify it is just like, what is the mass of the dark matter? Because the mass of the dark matter turns out to be a pretty important parameter in how you search for it. Here is a, here is a scale. It's going to be not very to scale in a moment, of where all the particles that we currently know about in the universe live. And dark matter could live anywhere within this scale and many orders of magnitude off the sides of this plot in either case. On the left-hand side at low masses, we know that dark matter could be as light as about 10 to the minus 21 electron volts. Between, as I think Fia talked to you last time, the constraints at the bottom end of this are just saying that the de Broglie wavelength of the dark matter should be small compared to galaxy scale. So we can actually fit individual dark matter particles inside galaxies. Up to about the keV scale, we also know that the dark matter has to be a boson of some kind, because if it's a fermion, Pauli exclusion means that you cannot pack the dark matter particles into small halos with sufficient efficiency to describe the structures that we see. So on my last lecture tomorrow, I'm going to focus on this cold bosonic wave dark matter and how we might look for it. Now, above the keV scale, we've got a lot more freedom. Dark matter could be a fermion, and it doesn't have to be super cold. Now, a large amount of the previous work on dark matter has been focused on this sort of GeV to TeV window around the electroweak scale, where most of the particles in the standard model that we know about live. So this I'll refer to as the traditional WIMP window. WIMP means weakly interacting massive particle. And there's been a lot of energy dedicated to that area, partly because of the possible connection between dark matter and supersymmetry and the hierarchy problem of the mass of the Higgs boson. But over the last decade or so, there's also been a great deal of interest in focusing on new light-dark sectors living at the MEV to GeV scale, and we'll talk about why that particular mass range is picked out and has become of additional interest. Below the MEV scale, dark matter usually has to be non-thermal in the sense that it was never in full thermal equilibrium with the standard model. We learned that from limits from Big Bang nucleosynthesis, as Valerie just told us about, and from bounds on N-effective. I'll talk a bit more about that later today. And there's another bound up at about 100 TeV, and we'll talk about where that comes from, that says that if dark matter was in thermal equilibrium with the standard model and is heavier than about 100 TeV, it's actually pretty hard to deplete its abundance to the observed value. So we have this sort of MEV to 100 TeV thermal window. We have this low mass region where the dark matter should be cold, non-thermal equilibrium, the standard model, and bosonic, that spans all the way down to 10 to the minus 21 EV. And then at high masses above the 100 TeV scale, we have structures like we have possible candidates that were never in thermal equilibrium with the standard model, going all the way up to the Planck scale or even higher, as in the case of the primordial black holes that we talked about. So from this bottom-up perspective, again, there's an enormous spectrum of possibilities to look for, spanning an enormous range of masses. We're going to need a large array of potential detection techniques to look for dark matter across this spectrum. So we recently in the United States went through a community planning process called SNOMAS, which we do about once every 10 years. And this is the cartoon from the latest SNOMAS process about this sort of bottom-up picture of the parameter space. Now, this is a cartoon. Don't take it too seriously. But this is also a bit of a forecast of what I'm going to be talking about over the next few lectures. So I wanted to show it. So the x-axis here is the same kind of x-axis that I just showed, the mass of the dark matter. The y-axis here is a measure of the interaction strength between dark matter and the standard model. This green region down at the bottom is the possibility that the dark matter might not interact with the standard model at all, or any way that we can plausibly measure. And we still, as Kfir has already talked about a bit, and we'll talk about a bit more, we still have constraints on the properties of dark matter in that regime. At the high end, dark matter could be macroscopic, could be compact objects that we can probe through gravitational lensing and the like. But in this range where the interaction strength is somewhat larger, we have a large ensemble of experimental techniques to try to search for interactions between dark matter and visible particles. Within this range, there are going to be regions of parameter space that we like to look at benchmarks for the dark matter particles. This is, there's the QCD axion, which I'll talk about more tomorrow. And there's the range of scenarios that are sometimes referred to as thermal dark matter. And within that, as a subset of that, is the classic WIMP. There's also sterile neutrino dark matter is another benchmark that is very often used. But more broadly, there's this huge parameter space to go after. The way that we're approaching that challenge experimentally is to try to both, so the tagline out of SNOMAS was delve deep, search wide, with the idea being that we can do experimental searches to try to target regions that we think are particularly interesting, theoretically, such as the QCD axion, the classic WIMP, the thermal relic targets. And but at the same time, we should recognize that actually dark matter could live anywhere in this space. It could populate this enormous range of masses and this enormous range of possible interaction strengths, and we should keep in mind searches that can provide generic constraints on this space. So these little gray regions are, again, a cartoon of the kinds of constraints that we currently have on these parameter spaces. We have limits on ultralight dark matter from Astrophysics and Cosmology, and dedicated axion search experiments have started to probe the QCD axion over a very shallow mass range. And again, this is just setting the scene, the big picture. We'll go into all of this in more detail in the next few lectures. Over in the particle dark matter range, we have direct detection and indirect detection experiments that have carved out significant chunks of the possible parameter space for thermal relic dark matter, but there's still a lot of open space. Over the next 10 years, and I'll try to persuade you about this in my next topic, we have the potential for experiments that will really probe the QCD axion over a large amount of its mass range, and will push down and will push deeper down into this thermal region, including covering a large fraction of classic WIMP benchmarks. Okay, but so the general strategy is try to hit the theoretically motivated regions, at the same time recognize that theoretical motivation may not actually be an accurate guide to how the universe is behaving. So let's see what we can do more generally. All right, so in my last 10 minutes, of this morning, well, of this lecture, we'll come back after the coffee break. What I want to talk about is the thermal relic target, and this hopefully should be a review since I think this was already discussed a bit in the lectures last week. So a lot of dark matter model building is informed by the question of whether the dark matter was ever in thermal contact with the standard model after the epoch of inflation. So the nice thing about dark matter models that were once in thermal equilibrium with the standard model is that coming into thermal equilibrium washes out a lot of information about what was happening in the UV, about what was happening in earlier times. So that means that the abundances are determined through their standard model interactions rather than through some UV initial conditions that we don't know about, which is both nice and predictive, and it provides targets for experimental searches. So typically in these models we're going to populate dark matter masses at the keV plus scale to avoid bounds on warm dark matter. And the classic and simplest scenario is thermal freeze out, and its many variations, although not the sole one. Okay, so let's do the calculation. So the picture here is, let's suppose in the classic scenario, the dark matter can annihilate to standard model particles through a two-body process. So two dark matter particles come in, a miracle occurs, this is what we'd like to understand, and standard model particles come out. If this interaction was strong enough, then sufficiently early in the universe, when the density was high enough, it would have kept the dark matter and the standard model particles in thermal equilibrium through annihilation. If this happens, then this is what we expect the generic history of the dark matter abundance to look like. When the temperature of the universe was significantly higher than the mass of the dark matter, then this interaction, dark matter particles colliding to make standard model particles, and the reverse process should both have been relatively rapid. So if the dark matter wasn't already there, this reverse process would populate it. Once the temperature of the universe, this is this phase one up here, this y-axis is the co-moving number density of dark matter, this x-axis is a measurement of time. Strictly, it's the mass of the dark matter divided by the temperature. So once this ratio drops below 1, once the temperature of the universe drops below the dark matter particle mass, the dark matter can still annihilate efficiently, but it can't be efficiently produced. At that point, its abundance will start to deplete exponentially. It's still in equilibrium, it's just following the Boltzmann distribution for mass of particles in equilibrium, which has an e to the minus m over t factor on it. And if we didn't live in an expanding universe, that would be the end of the story. But since we do live in an expanding universe, there's another mass scale, there's another scale in the problem, which is the time scale for expansion. Because the abundance is falling exponentially, the annihilation rate will also fall off exponentially, and eventually the timescale for annihilation will become comparable to a Hubble time. So heuristically, you can think of this as the Hubble expansion is pulling the dark matter particles together more rapidly than they can find each other to annihilate. So at that point, the dark matter abundance, the co-moving abundance flattens out. The subsequent depletion of dark matter abundance is just the 1 over a cubed scaling that you expect to have for non-interacting matter, and you get a plateau, which we call the thermal relic density. And the level of this thermal relic density is set completely by the annihilation rate. If the annihilation is rapid, you stay in thermal equilibrium for a long time and there's not very much dark matter left in the late universe. If the annihilation is slow, you end up with lots of dark matter left in the late universe. So because we have measured the amount of dark matter left in the late universe, we can reconstruct what annihilation rate you need, and it's about 2 to 3 times 10 to the minus 26 centimeters cubed per second, or in particle physicist units, roughly, it corresponds roughly to a weak scale cross-section. Okay, so I know you saw a version of this calculation last week, let me just show you my version of this calculation. So the ingredients that go into the calculation are the annihilation rate for identical particles, which if we look at the number of annihilations per unit time, per unit volume, that's going to go like the number density of the particles squared multiplied by the annihilation cross-section. And this factor of 2 here depends on whether you have identical particles or a dark matter particle antiparticle pair. So then let's assume that we have identical particles for the moment. So that's the annihilation rate. Each annihilation depletes 2 dark matter particles. So the rate of particle depletion through this annihilation is just n squared times sigma v. So that is going to give us the Boltzmann equation, which you can do through writing out the full Boltzmann equation and taking moments of it. But you can intuitively tell sort of has to have a form like this. dm by dt, so this is the rate of change of number density over time. If there were no collisions, it would just be minus 3hn. That corresponds to the dilution with the Hubble expansion. In the presence of expansions, we're going to have this negative term that depletes the dark matter density, which is minus sigma v times n squared. So this is the annihilation rate per unit time per unit volume. And then we're going to have another term, a compensating term, that comes from the production process. So it comes from standard model particles crashing into each other and making dark matter particles. In principle, that could depend on the standard model bath and it could be complicated. But since we know that when the dark matter, if the dark matter and the standard model were in perfect thermal equilibrium and there was no cosmic expansion, then the forward and backwards rates should cancel each other out. We can infer that this term needs to be minus the equilibrium value of the dark matter density squared, so that these two would cancel each other out in thermal equilibrium. We know what the equilibrium density is for dark matter. I'm going to assume that we can ignore the difference between fermions and bosons for the purposes of this calculation. So I'm ignoring the plus or minus 1 in the denominator of the Boltzmann distribution. So we'll just use the standard Boltzmann distribution instead. There are some circumstances where that approximation isn't good, but for the sort of standard thermal freeze-out scenario dark matter candidates, this is usually a pretty good assumption, that we're not in the degenerate limit. So we know how this equilibrium result behaves, and we're going to assume that this freeze-out happens in radiation domination. That's the standard story. You can have modified models where there's early matter domination and the freeze-out happens during that, but for the moment we'll assume radiation domination. In that case, we know that the Hubble parameter squared is proportional to the energy density, which is proportional to T to the 4. So that tells us that the temperature of the universe should be proportional to the square root of the Hubble parameter. Okay, so those are the ingredients that we're going to need. So if you want a precision solution, you basically just have to solve this differential equation numerically. You need to take into account that the evolution of the temperature of the universe includes changes as the number of degrees of freedom in the radiation bath change. You can do this calculation in detail, and it's done, for example, in this paper by Steigman et al. In 2012, and you get the cross-section that I mentioned to you before, gives you the right relic density, about 2 to 3 times 10 to the minus 26 centimeters cubed per second. But let's just do a simple estimate of the important quantities. So the freeze-out occurs when the expansion timescale is comparable to the collision timescale, so when h is comparable to n sigma v. So that's essentially just requiring that this term here, this expansion term, is comparable in size to this depletion term, n squared sigma v. So that defines freeze-out. Up until the freeze-out point, the number density of the dark matter basically traces its equilibrium value, so we require that the Hubble parameter at freeze-out is roughly n sigma v at freeze-out, so that's this equilibrium value times sigma v. And after freeze-out, we expect the dark matter density to just scale as a to the minus 3 as the universe expands. Now, we're going to note here, okay, so when this freeze-out condition happens, this happens in the context that the dark matter abundance is dropping off exponentially. So that means that like h at freeze-out or the sigma v that you need for freeze-out is going to be, exponentially sensitive to this ratio m over t. So we expect freeze-out to occur for m over t that is not super different from 1. Like if we wait sort of 100 e-folds after the dark matter starts to freeze out, the density will be really, really tiny. Another way to say that is that we expect the temperature at which freeze-out occurs to basically be log-dependent on other parameters in the problem. So we can make that a little bit more precise. In a scenario like this, the original number density of dark matter particles before the freeze-out happens should be comparable to radiation, okay? Because it's just a relativistic species in the early universe. Its number density would just be like t cubed times some factor depending on the number of degrees of freedom. So unless it has a huge number of degrees of freedom, it should be similar to that of radiation. But today, so how does the number density of dark matter compare to radiation today? Well, it depends on its mass. We know that there's about 5 GeV of dark matter mass per baryon in the universe, and we know that there's about 6 times 10 to the minus 10 baryons per photon in the universe. So that tells us that there's about 3 eV of mass in dark matter for every photon in the universe today, okay? So that tells us what? If the dark matter is 3 eV, we didn't need to deplete its abundance at all, okay? The number density in the present day would be similar to the number density that you would get from the early universe just from saying it has a similar number density to radiation. And we expect this number density of, number of amount of mass in dark matter to one number of photons to be roughly constant after freeze out. It won't be perfectly constant because there are processes that inject more photons into the universe at early times. But roughly at the order of magnitude level, it should be pretty constant. So if dark matter is a lot heavier than 3 eV, say dark matter is 3 GeV instead of 3 EV, that means that its number density today is about 9 orders of magnitude smaller than that of the photons. So from the pre-freeze out epoch, when it had a similar number density to photons, to today, its abundance needs to be depleted by 9 orders of magnitude. That's what that exponential suppression has to do for you. Now, that exponential suppression is going to be roughly e to the minus m over t. That's the exponential factor that drives the dark matter abundance down a lot. So what we'd suggest is that that means that this e to the minus m over t factor has to be roughly the suppression factor, which is the mass of the dark matter, which is the EV scale, divided by the mass of the dark matter. So if we estimate, okay, so what should this ratio m over t appearing in this exponential be? It should be roughly the log of the mass of the dark matter divided by 1 EV. If we said the dark matter was like 1 GeV, okay, that means we need to drive down its abundance by 9 orders of magnitude. That corresponds to the minus m over t factor in this exponential being roughly 20, because e to the minus 20 is roughly 10 to the minus 9. This is incidentally very similar to the CMB calculation that we just talked about, and why the why the photons decouple from the electrons at 0.3 eV instead of 13.6 eV. It's more or less the same factor of 20. It's just, you need to, you could, in the CMB case, it's only the photons out on the tail of the Boltzmann distribution can ionize hydrogen with its 13.6 eV ionization potential, but you've got 10 to the 9 times as many photons as you do hydrogen atoms, so you can get down to about an e to the minus 20 suppression in the tail before you don't have enough photons to ionize stuff anymore. Similarly, here, we want to deplete the dark matter abundance by 9 orders of magnitude. We need e to the minus m over t to be about 20 for GeV scale dark matter, and it depends just logarithmically on the mass of the dark matter. Okay, so that's roughly when freeze out happens, about a factor of 20 below the mass of the dark matter for GeV scale stuff and scaling logarithmically with the dark matter mass. Now, to estimate the required cross-section, we can do another little trick. We can use the condition that at freeze out, the Hubble time, the h is about n times sigma v, and also if we're in radiation domination, then h roughly scales with the temperature of the universe at freeze out squared divided by the Planck mass. After freeze out, the number density of dark matter is just diluted with the expansion of the universe, and at matter radiation equality, we should have the total mass density of dark matter, so the mass of the dark matter times the number density at matter radiation equality, should be roughly equal to the radiation density at matter radiation equality. Last slide. Yes. Yeah, I have some bonus slides, which is the more complicated version of this calculation. I won't do that today. I'll leave that as an exercise for the student. So we'll just stop here. But so at matter radiation equality, the energy density in radiation and the energy density in matter should be similar. That's what we mean. So I'm going to parameterize the amount of dark matter in the universe by the temperature at which matter radiation equality occurs, which is what I mean by this TMRE. Again, I'm going to just ignore all the things that heat the bath or cool the bath besides the expansion of the universe. So under those circumstances, the temperature is proportional to just 1 over A, like 1 over the scale factor. And so then we can write this set of things. So the cross-section that we need is the Hubble parameter at freeze out divided by the number density of dark matter at freeze out. That's what this condition says. We can get the Hubble parameter at freeze out in terms of the temperature at freeze out, which we've just said is m over 20 via this relation. And we can get the number density of dark matter particles at freeze out by just rescaling the number density of dark matter particles at matter radiation equality back to the freeze out time. So then we'll plug these numbers in, we'll do some simplification, and we get a result that looks like this. That the cross-section that we need is going to be this ratio of the mass over the temperature at freeze out, which we said before is about a factor of 20, divided by the Planck mass, which tells you about the expansion of the universe, and the temperature at matter radiation equality. So this is a dimensionless number, and around order 10 for GeV scale dark matter, order 1 if you want to go to lower masses. And this sets the overall scale of the problem. The temperature at matter radiation equality is measured to be about 1 eV. The Planck mass is about 10 to the 19 GeV. So the sort of characteristic mass scale here is the geometric mean of these two numbers, which is about 100 TeV. So that's the cross-section that you need. All right, So I'm going to stop there for the moment, let everyone go get some coffee, and I'll take some questions, but when we return after coffee, we'll continue talking about the implications if you did have this kind of origin story for dark matter in the early universe, what would happen next. Thanks very much.
Okay. Any urgent question? Yes.
So maybe this is a bit of a silly question, but assuming that dark matter exists and it's made of particles like baryonic matter, if dark matter only interacts through gravity, is there any hope of ever determining in an experimental way if dark matter is composed only of one type of particle or many particles? Because if gravity is the only force that dark matter is able to feel, then aren't we kind of blind when it comes to its properties and its interactions?
Yeah, so good question. So I mean, the hope, of course, and maybe I could have made this clearer on this slide. In most of these scenarios, dark matter doesn't only have gravitational interactions. So we have good reason, I think, to hope and if you think about, how dark matter gets its abundance in the present day universe, that very often suggests some interaction other than gravity. It's not a theorem. Dark matter could be purely gravitationally interacting, but we have, I think we have good reason at least to hope that there are non-gravitational interactions, and non-gravitational interactions would be the tool that you can potentially use to disentangle this problem. That said, so let's go with the, no gravitational interaction. No non-gravitational interactions. Or very tiny non-gravitational interactions. We are in the green region of this plot down the bottom, where we just have some kind of secluded dark sector. So then it's going to be hard. So I guess there are two cases, one harder than the other. So you might say, what if dark matter has no non-gravitational interactions with the standard model, but it does have non-gravitational interactions with other dark matter particles? Then I think there's some hope. In particular, if you had different dark matter components that had different properties with regard to self-interaction or with regard to how fast they're moving in the early universe, you could hope to try to tease that apart from structural formation, although it's going to be hard. One of my colleagues who's a string theorist asked me about this a few years ago because he likes to think about models where there are sort of multiple secluded dark sectors, but each of those dark sectors can have significantly strong self-interactions. You might imagine, something like the bullet cluster system could sort of act like a filter for different kinds of dark matter then. Like you'd have the standard model gas clumps in the center with the strong interactions, and then more weakly interacting dark matter would have slowed down by a bit, but not as much as the standard model, and dark matter with only gravitational interactions would hardly have slowed down at all. So then if you could do a really good observation, and combine this with other probes of self-interactions like small dwarf galaxies, maybe you would be able to sort of separate out the different components then. If there's really no interaction except for gravity, so I think the true nightmare scenario is there's no interaction except for gravity. The dark matter particles, none of them have large de Broglie wavelengths, and none of them are fast moving from the early universe. So, we're all, like maybe if we've got two candidates, one of which is, 10 eV and the other one of which is 100 GeV, then and they're both really cold and they've never been in thermal contact with the standard model. That I think is really hard. Like maybe somebody else has a better idea, but I think that's the actual observational nightmare scenario. But again, if in that case, I mean, the one thing that makes me hope that that is not the case is that it's very surprising to me then in that scenario that dark matter and standard model particles.
For their wonderful talks and lectures, and let's go for coffee.